Good afternoon, and thank you for joining us for the 51st webinar in the Offshore Wind series, Learning from the Experts. I am Jana Herndon, a Senior Project Manager with NYSERDA's Offshore Wind team, and it's my pleasure to be joined by today's expert, Dr. Sarah Corbis. Before I introduce our speaker, a few reminders for participants and some background on this webinar series. Next slide, please. If you are experiencing any technical issues, please contact Adam Hauk at the email address on the bottom of this slide. This webinar is being recorded, and the recordings and presentation slides for all webinars in the Learning from the Experts series are available on NYSERDA's website at the address on this slide. All participants have been muted. We will have time for Q&A following the presentation, so please use the Q&A function to submit your questions to all panelists. Next slide, please. New York State is working to advance the responsible and cost-effective development of at least 9,000 megawatts of offshore wind by 2035. Offshore wind is a critical component in achieving the state's goals of 70% renewable sources of electricity by 2030 and 100% zero emissions electricity by 2040. While offshore wind has been providing clean energy to other parts of the world for several decades, this industry is brand new to New Yorkers. To provide interested stakeholders and members of the public with accessible, impartial information and opportunities for engagement on specific topics of interest, NYSERDA is hosting this educational webinar series called Learning from the Experts to connect the public with independent experts in key topics in offshore wind. We endeavor to select Learning from the Experts speakers based on their expertise, not necessarily for an alignment of opinions with NYSERDA or the state of New York. If you would like to suggest a topic or speaker for a future webinar, you can email us at offshorewind@nyserda.ny.gov or fill out a survey also available on our website. Please note that the views and opinions expressed in this presentation are those of the presenter. Next slide, please. It is now my pleasure to introduce Dr. Sarah Corbis. Dr. Corbis is a senior scientist with Worley Consulting and has been working in marine science and regulation for over 25 years. She focuses on marine protected species and specializes in impact assessment, permitting and compliance, and mitigation. Her work in offshore energy includes construction and operations plans, NEPA documentation and consultations, siting and planning, development of practicable mitigation, Marine Mammal Protection Act authorizations, and more. She's a member of the RWSC Technology Committee, is a steering committee member of the Oceanic Network Data and Digitalization Working Group, and is chair of the Technology and Innovation Working Group for the California Offshore Wind Monitoring Guidance Effort, led by the National Marine Sanctuary Foundation. It is now my pleasure to hand things over to our speaker. Sarah?
All right. Hello, everybody. I think we can just get started here. I'm going to look at my slides here as well. There we go. All right. So I'm going to talk a little bit today about sound and acoustic monitoring and focus mainly on technology. I'm Sarah Corbis, as she said. I work for Worley Consulting, which in my role, I am one of our environmental leads. So I focus a lot on permitting and planning and compliance. And next slide, please. So a quick overview of what we're going to be talking about. We're going to talk a little bit about the impacts of sound, some of the mitigation and monitoring technologies that can be used to address impacts, how offshore wind industry is applying some of these technologies, a little bit about requirements and incentives for the industry, as well as effectiveness and technology standards. Next slide, please. So we'll start with impacts of sound. Next slide, please. So this slide provides some information about sources of sound during there's different phases of offshore wind. You have the pre-construction phase where you're doing site assessment and collecting data, such as doing geophysical and geotechnical survey work, which is kind of depicted up in the top right corner there. And then there's also installation of the actual wind farm structures, which in the case of fixed wind is often accompanied with pile driving, but to put in the monopiles or the jackets that are going to hold the turbines. In the case of floating wind, that's usually installation is usually going to involve some kind of anchoring to place moorings that will hold the floating structures in place. And then in the long term, after installation, which also includes cable laying, which does generate some noise, then you also have the operational sound of a wind farm operating over time. I want to point out here that in terms of the geophysical survey work, the picture that I have up in the top here is from National Oceanic and Atmospheric Administration. There's been collection of this type of data for many, many years. This is a very standard practice to use high resolution geophysical equipment to do particularly bathymetry, like any bathymetry map that you look at that shows you how deep it is wherever you are in the ocean. These data are collected by ships that go out and use sound sources to collect those data. So NOAA, as well as the National Marine Sanctuaries, the Coast Guard, the U.S. Geological Survey, National Science Foundation, all kinds of organizations have been collecting data all around the same areas where offshore wind is occurring. We need a higher resolution data for engineering offshore wind farms and for taking data to understand what the habitat is in the area, as well as to look for things like any archaeological artifacts or sites, or unexploded ordnance, which unfortunately is something that's around in the ocean from various sources. So there are other data that need to be collected than the ones that have been historically collected, but it's the same types of equipment. These are not anything that is new. And there's been a lot of mis and disinformation around the effects of this type of sound on marine mammals. This does not kill marine mammals and is not responsible for marine mammal strandings on the East Coast or anywhere else in the US. So if you want to learn more about what the issues are around strandings, I'm happy to talk to you in a separate situation. Feel free to contact me. I have an email at the end of the presentation here. But I wanted to make sure we talked about that quickly. All right, next slide, please. So what are the potential impacts then? Well, potential impacts for animals in general, you can have changes in behavior. Usually if you have a short-term sound source like a pile driving effort, those changes are short-term as well. Masking, well, it means that the sound itself could make it hard to hear other sounds that you might need to hear. So like if you're in a crowded room and lots of people are talking, it's harder to hear the person you're talking to than if there's no one around you making other noises. It can cause animals to avoid an area. And again, if it's temporary sound source, usually that'll be a temporary avoidance. But if you have long-term noise, then that can sometimes create some areas of displacement that are longer term. You can also have effects to animals' prey. So it's important to understand both what the direct effects are on the animals themselves, like for example, if you're interested in sea turtles, and then think about, well, if it affects their prey, of course, that can also have an indirect effect on your species of interest. When it comes to animals like invertebrates, there's the potential for disruption of settlement for those animals that are sessile and settle out of the water column, things around growth patterns, or even in that case, maybe injury or mortality. This is, again, not something you have expectations for animals like whales or sea turtles, but there are other types of animals in the ocean. So making sure that we're considering all the potential effects to animals so that we can do the best we can for mitigation. And I think one of the things that we like to distinguish in this context is acute, sort of an acute stimulus that could affect animals, like again, pile driving, versus something that's chronic, that'd be ongoing for an extended period of time, like some kind of operational noise. Next slide, please. So when we think about potential impacts, there's a few different levels of impact that are important to consider. So there's individual effects. So like I said, if there's an invertebrate that is right next to your pile driving effort, maybe it is injured by that effort. That's an individual. But then you ask yourself, okay, what does that mean from the context of population level effects? Because you're dealing with populations and ecosystems, and then also cumulative effects. So cumulative effects are more of an aggregate of effects. So if there's effects to the animals from other things that are happening, maybe there's some other threat or pressure, climate change, for example, adding that into this additional stressor of sound is something that needs to be considered. And we try to do that often through different types of modeling assessments. So I have an example here that I pulled from the Docet site. You guys may have seen Docet's presentations. And so this kind of gives you a generalized idea of thinking about what's the stressor, what are the reactions to the stressor. In this case, it's broken down by physiological or behavioral responses. And then how does that affect the health of individuals? How many individuals are likely to be affected? How would that affect their fitness, meaning how they reproduce and how many offspring they may have? Is this an acute or chronic type of stressor? And all of that gets put together with data that we have from actually monitoring different types of species and doing research on how these things affect at the population level. So looking up further from than just the individual and thinking about, will this matter to the population as a whole? Next slide, please. So once one establishes what are the potential impacts, then you make determinations about priorities for severity and probability. You know, what is the likelihood that some particular effect may occur, and how severe is that effect? And then you use that to help you develop mitigation and monitoring strategies to help minimize or avoid impacts. And in some cases, if they can't be minimized or avoid, potentially offset them or restore after the fact. We call it the mitigation hierarchy. And so there are different ways that you can go about trying to address potential impacts. There really is no way that you can produce energy without some kind of impact. So we expect that there will be impacts from any kind of structure on land or offshore that is put in place to help us collect and transmit and deliver energy to people. But we want to make sure that those impacts are minimized and that those impacts aren't likely to cause population level or ecosystem level effects. Next slide, please. So I like to distinguish between platforms and what maybe you could refer to as sensors in the context of the technologies around mitigation and monitoring of sound. The platforms are more like the thing you're deploying with. So you may have lots of different types of sensors that you use, but you could put them out on, you could be using them based on a traditional vessel, say towing some kind of array. You could put them on infrastructure like directly on the wind turbines themselves or the foundations. You could be using remotely operated vehicles or autonomous vehicles, drones. You can put things on buoys that are placed. Even on animals themselves, you can see a picture here of an animal with a tag on it. So the platform is sort of where you're going to put the equipment that you're going to use to collect data. And you can see this equipment is starting to get very sophisticated. One of the nice things about offshore wind is that it has driven a commercial scale of scientific research equipment effectively. So as a marine mammalogist by training and background, you know, a lot of the types of equipment that we use or even the platforms are things that people kind of like build in their basement. Basically you say, okay, I'm interested in learning about acoustics and marine mammals. I've got to get an engineer to work with me and we've got to make a tag or we've got to make a sensor that we're going to put out on a buoy because there just aren't commercial things easily available, or if there are things that other folks are willing to sell to you, they may not be well supported. You know, it's not like companies per se, it's other researchers who are helping to distribute this type of equipment. So this has been really valuable for getting consistent equipment, access to equipment, more types of equipment available, improvements to the equipment to help us be able to get more data even outside of what wind farms are gathering. You can see a really cool one down the bottom here is a drone that goes underwater and in the air, which I just think is really an amazing technical feat. Next slide, please. In addition to the platforms, and we'll talk about sensors a little bit in a moment, there's also sound reduction technologies. So part of mitigating for sound is to try to produce less sound or to keep the sound contained. So you can see here as some examples in our pictures, and there's a list of things in the slide, but there's a picture here at the top of a bubble curtain. So when you pile drive, you're producing sound by, you have a pile in the ground and you're basically hitting it with a hammer, and that hitting creates noise. So these bubble curtains are basically just equipment that's laid out on the bottom and creates a wall of bubbles. It runs air through it to create a wall of bubbles that will dissipate the sound. So as the sound propagates out from the pile, it sort of interrupts the sound as it goes so that it won't travel as powerfully or as far. And you can see that sort of what it looks like around a pile driving effort there. This has really been a huge value for pile driving, certainly. And we've used this type of technology, and cofferdams is another one of sort of like to physically block sound. Historically, the technology has been improving, again, with offshore wind, both in Europe, and in other places in the world. There's been a lot of work toward improving these technologies, and they're getting better and better all the time. And we're also doing a lot more research to understand how well they work in real life, rather than just in modeling or in small scale sort of efforts to assess that in places like in a lake or something. Then also there's on pile types of sound reduction, which folks aren't always aware of. So the picture in the middle is one of those types of systems. So that actually is meant to absorb some of the energy on the pile itself, so it doesn't go out into the water column in the first place. So that's another way that we can reduce sound. And then on the bottom, the picture there is showing you one of the AUV type glider systems under the water. And so in the case of, we had talked earlier about how there's sound that's used to collect information about the bottom. That can be done from the surface. You can have a vessel that's traveling at the surface and towing that sort of system to send sound down and receive sound and get the information. Or you can potentially use, in some cases, AUVs, which can be closer to the bottom. So that puts less sound in the water column itself, because the AUV is now near the bottom instead of at the surface. So these types of systems like AUVs can also be really good for mitigation purposes in a manner of speaking, or reducing or avoiding noise impacts. And there's a variety of other things that are applied. I think seasonal operations is another thing that's common. Some of it can revolve around the animals themselves, like when animals are present that you think have sound sensitivity, you could choose to have hiatuses in operations. Another way to look at this, though, too, is that there are different sound speed profiles. Sound travels differently in different conditions in the water. So different temperatures, for example, affect the speed and directionality, and different things about how sound moves through space. So there are different times of year, or different conditions really, under which sound will travel further or not. So you can think about those aspects of actual sound movement when considering when and how you do different types of installation, for example. Next slide, please. So one of the major tools that we have in monitoring and mitigating for sound impacts is passive acoustic monitoring. Passive acoustic monitoring, also referred to as PAM, which I probably will say because I'm used to the shorthand of it. This can be either real-time or archival type data collection. In real time, we often use it for actual real-time mitigation, and I'll talk a little bit more about that. These systems can be deployed on a moving source. So for example, on a vessel towed behind, which you can kind of see in the picture on the bottom there to the left, and then on the bottom right, there's a moving source where it's an autonomous vehicle that's moving around in space and can collect sound data. So these kind of, again, become the platforms, and then you have the sensors that you want, in this case, passive acoustic monitors, which vary depending on what you're trying to monitor. So there's different frequencies that ambient noise or animals may be making noise in. So you're going to need to adjust and adapt your equipment to be able to detect the types of noise that or sound that you're looking for. And then there's fixed buoys, for example, in the picture there at the sort of middle of the page. So you actually would attach such a thing to the bottom, and then you have a stationary monitor. You can see in the right side here of the slide that there's also quite a bit of passive acoustic monitoring work that is ongoing on the U.S. East Coast. I think this is maybe an undersold advantage of offshore wind. On the one hand, of course, there was research going on using acoustic monitoring on the East Coast prior to the advent of offshore wind projects, but this has really grown since offshore wind began to be an interest on the East Coast and lease sales and such. The sort of yellow spots on there even indicate where there's been glider coverage. A lot of that coverage there in New York Bight area and such, that's driven by companies that have paid other, the wind industry has paid companies to collect these types of data. There's also, of course, the Regional Wildlife Science Collaborative and the Responsible Offshore Science Alliance, which are two organizations that have grown out of the offshore wind industry and are doing research and creating standards and understanding data gaps and helping to coordinate things like these large regional scale efforts, which if you're going to look at passive acoustic monitoring across this whole swath of the East Coast, these are efforts that require large collaborations, and we'll talk a little bit about standardization in a later slide. But a lot of this work is actually being driven by offshore wind at these scales now, because those data are necessary not just to inform a wind project, but also to understand potential impacts. And the nice thing is it's still applicable to other types of research that aren't necessarily driven by the wind industry. Now, if you want to monitor for animals in order to enact mitigation measures, which we'll talk about some of the traditional mitigation measures in a moment, you're going to want to use different types of equipment than just passive acoustic monitoring. I noted here, for example, satellites. I'll show you some pictures here in the next slide. Let's just go ahead and move to that. So other monitoring equipment can include a variety of different types of cameras, and there's thermal and infrared type detection devices. Depending on what you're trying to detect, radar. There are some concerns in some places about sound and birds. Radar is commonly something that's used for bird detection. You can directly tag animals. And also, this is super interesting. You can see here that in the pictures, there's been a lot of work undertaken on evaluating the use of satellites for whale detection. So you can see there's two different examples here of right whale, and these whales being detected by something, a drone or a plane or whatever it is, and then what this looks like when compared to the satellite imagery that can be downloaded. Now, this requires, of course, having algorithms to detect such signals. Same with passive acoustic monitoring. If you have all these reams of sound data, you have to be able to detect the things you're looking for within that. So there's been a lot of focus on developing algorithms for that detection and then identification or classification to particular, like you say, oh, that's a whale sound, but which whale? Oh, that's a fin whale because it has these particular characteristics in the sound. And if the question that you need to answer is related to where the animals are in space, when you have a passive acoustic monitoring system, it'll have a radius around it in which detection can occur. So maybe you could hear a baleen whale from 40 kilometers away. That wouldn't be unreasonable in some situations. So you have this sort of radius of 40 kilometers around the PAM buoy, let's say, that animal could be. If you want to know more specifically where it is, you can use additional hydrophones, additional PAM systems that will triangulate on animals, because the speed of the sound reaching the different systems varies depending on where the animal is in space. So you can triangulate it on its location. So if that's important, that's something else that you need to set up methodologies and systems that are capable of identifying that and being able to localize the animals. Artificial intelligence, I think, is going to be an interesting space to start looking at, how we might be able to use that to create better detection. In some cases, there's still a lot of hand work on these things, you want to try to make algorithms that at least detect where you think there's a signal of importance, because there's a lot of data, but you have to sit down and look at everything. And of course, you'd always double check a subset of data, but in an ideal world, you are able to develop sufficient algorithms or artificial intelligence approaches to pull out all the signals that you want fairly quickly. And that helps you do more real-time monitoring too. If you're monitoring for right whales, for example, with a buoy that's meant to immediately basically send a signal to a satellite that tells someone there's a right whale there, you want those algorithms to be fairly good and reliable, and be able to translate quickly when they find something they think is important. Let's go to the next slide here. So now that we've talked a little bit about the monitoring technologies, let's kind of talk a bit about how they're used by the offshore wind industry in particular. So I've pulled a number of examples, and there are certainly many more examples of this. There's, as I noted, there's quite a bit of research that's been ongoing. There's a lot of work with the academic researchers and the agencies that conduct research and manage resources in the ocean for the offshore wind industry to understand, again, how to minimize its impacts, how to have site well, and also even just more generally reduce potential impacts or create conservation opportunities for marine animals and habitats. An example here of some of the things the offshore wind industry has been doing in the technology front include different types of foundations that don't require the same amount, or in some cases maybe any, pile driving to be installed, and that can significantly reduce the amount of sound that's produced in the installation process. So it's an example of that there on the left. There's also the passive acoustic monitoring we talked about. This slide has another picture of what that looks like. This picture comes instead of from NIMS or the National Marine Fisheries Service. This picture actually comes from the Regional Wildlife Science Collaborative, which includes a lot of those same buoys, but also some other research efforts that RWSC is tracking. On the right side, we see buoys, and there's some whales there making noise. So the buoys that are put out either directly for the purpose of monitoring whales, or buoys that are put out by industry in order to collect mid-ocean data, because they need to understand wind and waves and currents and things like that for construction purposes, and maximizing the energy production. And those platforms can include a variety of different sensors that can collect other types of data, such as whale vocalizations. And so there are a number of different projects that are using that as an advantage. Also, offshore wind industry has been investing quite a bit in technological development of autonomous vessels. Part of that is, of course, for better data collection. For example, as opposed to like a person looking at things, you can operate an autonomous vessel at night or in poor weather conditions that you might not be at sea. It also is a safety promoter. You know, like the less people you have physically on the ocean, the better off you are in terms of safety. There's always risk that comes with being out physically on the ocean or on a boat. So these types of autonomous systems can be really helpful. Next slide, please. So I mentioned RWSC several times. They actually, I just got an email, I think yesterday or the day before yesterday, that they have a final report out now on their whale detection technology evaluation workshop series. So the picture on here is of one of the sessions, the title page of their session notes, but they have a final report that's now available. So this is something that RWSC has been spending some effort on gathering together and getting experts. So if you're interested in this topic, I highly encourage you to go to their website. They've also been collaborating with the Marine Technology Society Journal and a variety of academic institutions on TechSurge. And for example, Rutgers University has been working with the wind industry and RWSC, and is looking at how what kinds of data can be collected from the platforms of opportunity that are created by offshore wind structures, and what kinds of sensors and technology we need in order to be able to do that well. We also did a project ourselves on for the National Offshore Wind Research and Development Consortium. And that project, we've collaborated with the Biodiversity Research Institute to look at what technology gaps are to being able to collect scientifically robust data to answer the scientific questions around impacts and efficacy of mitigation, for example, for marine mammals and birds in particular, and baseline data and things like that. Being able to integrate that also into the infrastructure and operations. And that reduces cost and reduces safety risk and just makes projects certainly better if they can be integrated directly into what's already being done. If you already have a platform out there, like a buoy, for example, if you already have a vessel out there, how can we take advantage of that to improve our data? And what types of technology do we need to do that? So we identified, that report is out, and there is a journal article in Marine Technology Society journal kind of outlining some of our findings from that study and what types of improvements we need in the technology itself. And that can drive and has driven some work by NowRDC and perhaps others in looking at, what do they fund or what do they ask people to do from a technical perspective for submitting for grant applications and things like that. Next slide, please. And then the offshore wind industry just has been doing a lot of research more generally, and I won't go through all of this, but I wanted to share some of the things that are being looked at that and sort of can be direct. There might be direct efforts at looking at ways that to reduce the risk of vessel collision, for example. And there may be some things where they're collecting data that can just go into larger pools that other people are asking questions about, like what are some of the drivers of animal distribution related to mid-ocean data, and so things like currents and dynamic habitat variables can affect how animals distribute themselves in space. Well, the types of data that are collected by offshore wind farms can help inform that. Passive acoustic monitoring is a good example, and you can see in the top here of this slide, the picture this comes out of NIMS analyses of some of the National Marine Fisheries Service analyses of some of the passive acoustic monitoring data that's been submitted, a lot of which is now around offshore wind. And then I do want to remind people that actually not all of this is about marine mammals, of course, and there are different types of acoustic impacts as well as acoustic data that can be collected on other species. So in the picture on the bottom, we see an instance where, in this case, fish have been tagged with an acoustic tag, and there are sensors out to collect data when those animals go by. There's a similar concept with birds and modus tagging type things. And so having tags on animals that can be detected, or, fish and some other types of animals do make sounds that in some cases that data can be collected as well. Some of the technology improvements that have been driven and are being driven by offshore wind involve the things you might imagine would be necessary to collect better data. You need more power or different tower sources. You need to have good data transfer. You need to have more capacity for data storage and archival systems. And you really want to have data that are higher resolution and higher quality than some of the broader things like we were talking about with bathymetry, for example. At the end of the day, there's a lot of modeling that has to happen to evaluate what's going to happen, even from the perspective of how do you install things in an engineering, for engineering in a sound manner. All of this needs certain amounts and types of data. So the offshore wind industry has been a really recent, heavy driver of technological innovation because there's commercial scale. When there's a commercial scale activity, then people have incentives to develop these technologies because they have a market for them. When all that you're doing is basic research, unfortunately, that's not really a huge market and doesn't drive a lot of the innovation that the offshore wind industry can. Next slide, please. So let's talk briefly about the requirements and incentives around mitigating and monitoring for sound. As an example here on this opening slide, you can see there is, this is just one of many pictures like this that are in offshore wind farm plans. This one happens to be from Revolution Wind's marine mammal monitoring plan. But basically, where there's a pile driving event, which is where the star is in the center, for each pile driving event, this is one of the sets of mitigation that is applied, and this is mainly directed at sound. So I've used this as an example here. So the little pink and blue arrow guys, those are vessels, and black, I guess they have several colors here, but those are vessels that are moving around within the sort of circles that are indicated for them. There's a certain amount of visibility expected, or that's necessary. In fact, you can't start operating unless you have sufficient visibility to do this monitoring process at this time. And so you check for marine mammals or sea turtles in these circles, basically. And these are actually fairly large distances. They may look small on here, but you're talking, multiple kilometers here. And so that is for clearance or shutdown. So you don't start pile driving if there are animals within certain distances. And then if you're pile driving and an animal were to enter within a certain distance, depending on the animal and what's going on, and if it's safe, you would stop pile driving and wait for the animal to get out of that zone. And so those are clearance and shutdown zones. And then these little flags in this picture are passive acoustic monitoring systems. And then the yellow circles are showing you what the range is of those systems. For identifying, in this case, a lot of the focus is on right whales. This is an East Coast project. So ideally at being able to detect right whales and other baleen whales at these distances indicated here. And again, that's used for clearance or shutdown or other types of mitigation measures, and understanding how animals are reacting or aren't reacting to the sound that's being produced. So there's quite a bit going on there. So there's a lot of effort that's put into, in addition to things like bubble curtains and other stuff we talked about on pile. There's a variety of things, but this is like one of the aspects. At the end of the day, there are literally hundreds of measures just aimed at marine mammals and mostly sound in the context of installing fixed wind. It's a very, very involved set of mitigations that requires a lot of coordination and a lot of people and technology. So there is a lot of work that's done to help prevent impacts to protected species in particular from offshore wind installation. Next slide, please. So some of the typical requirements that are in place to do that, in addition to just doing like that type of monitoring, which is indicated here with the clearance and shutdown type of mitigation. The first mitigation, of course, is really around siting. And so choosing siting that makes sense is important. The Bureau of Ocean Energy Management and other agencies work together on that to evaluate what are sites that have least conflict and risk as is reasonable, for also having sites that have sufficient wind and things to be able to be commercially viable. Then there's a variety of other things that are done to help reduce these impacts. Protected species observers, which you can see a person with this very giant binocular set up in the top here, is one of the things that's very typical. So those vessels that were in the previous picture that are going around looking for whales, they have third-party people, not just folks who are vessel crew, who are on the vessels with the job specifically of looking for protected species and implementing these clearance, shutdown, and other types of mitigation measures that are required through a variety of different permitting. And of course, Marine Mammal Protection Act is one of the protections for marine mammals, and requires its own separate permitting from Bureau of Ocean Energy Management permits. The technology has been improving, and there's a lot of, and again, offshore wind is driving a lot of that commercial scale. The oil and gas industry has driven a lot of that too, because that is a commercial scale activity that also employs this type of protected species observer monitoring. I like this that I pulled this picture out from a publication, but you can see the thermal technologies. So in order to be able to use these new technologies, it is actually really important to be able to get out into the field and do studies on them. So understanding, like you can see here what this technology looks like when you see the blow with your eyes, for example, of this whale, and then what it looks like in the thermal camera. The thermal camera will work at night, right? You'd see the same thing pretty much at night. There might be a slightly different temperature regime in the water or on land, but these things can be used for that. But you want to sort of ground truth this out of that. You're figuring out, okay, well, what does it look like? If I see a whale, what does it look like? Now that helps me to be able to create algorithms that help me detect whales or understand what I'm seeing when I see, a fluke in this hot spot that you see here. So you need to go out and do that kind of work. It's the same with passive acoustic monitoring. All these things, for them to detect an animal, you have to have something that if a human being isn't looking at every single piece of data, you're going to have to go out and say, okay, I see what species is here around this passive acoustic monitor, and we hear it at the same time. I know that's what that species, that sound signal goes with that species. I know that because I was out there and I collected that data at one time. Now in the future, when I have to hear that, I can be confident that that's the species that I'm hearing. So all those data are really important. And some of the work that's being funded by Offshore Wind right now is involved in sort of teaching algorithms and getting data that can help do that. In the bottom here, you can see an example from the National Marine Fisheries Service has set up a really great portal site where they're collecting a lot of the data from the passive acoustic monitoring along the whole East Coast. And this is an example of a sort of an output you can look at. Now you could go to this site yourself, open it up and choose a time and a place or whatever, and look at this type of thing, like how many whales, relatively speaking, have been detected in this particular time frame, etc. So this is a publicly available thing and is pulling in lots of different information across multiple projects. So this is part of those regional collaborations. RWSC is also focused on a lot of these. There's the NOW project that Duke University is doing, the one I mentioned from Rutgers. Lots and lots of large-scale collaborative work, heavily supported by the offshore wind industry, as well as, again, these platforms of opportunity that are going to be in the water where data can be collected on a longer-term basis, and looking at opportunities, for example, with Fisheries Service to be able to get more data and higher resolution data than perhaps in their case. Maybe they do a cruise and a survey with an airplane once a year or once every other year or something like that for a few weeks. That's it's expensive and difficult, and to do research at sea, but you could collect a lot more data over periods of time when, again, weather isn't great or whatever, that you wouldn't be out on the ocean that much, and you can get more data from these platforms that are out there. And that helps with long-term monitoring and adaptive management. If it seems like there is a problem, you can detect it sooner and be able to even if that problem isn't driven by offshore wind, like, it helps you understand population dynamics and distribution, climate change. You're collecting a lot of mid-ocean data and understanding what's happening on a much finer scale than we can do without having this platform of opportunity. Next slide, please. So then what's the incentive for the wind industry? I mean, why would they do all this research work? Why would they spend money and time on developing better technologies for monitoring, for example, or reducing sound? There are a lot of good incentives for them to do that. Not the least of which is that it does, the more data that they have, and the more they're able to provide an offset, for example, or information that helps for conservation or helps us understand what's going on with animals, the less mitigation burden that they may have in the long run. So eventually, you can hone in on the things that are genuine problems, and some of the things where we simply have uncertainties and we put into place mitigation to address those uncertainties, or we don't have a lot, we're using models, but we don't have a lot of in real life type data to verify that. As we get that, we can adapt our mitigation. One interesting thing that's being looked at now is in this top picture is distributed acoustic sensing, where there's going to be cables that are associated with moving the energy to shore. And so those cables have fiber optics and things and can potentially be used for actually collecting acoustic data and transferring that data. So this could be a very interesting way to have a network of of cables that actually is a network of sensors telling us more about how animals are using in space and are distributed in space. So that's a really interesting area of development. The bottom picture shows you nighttime pile driving in Germany. In the U.S. at this time, most of the projects aren't necessarily authorized for pile driving at night, and there are some uncertainties around implementation of mitigation. So some of these technologies are meant to be able to do a better job of detecting animals in low visibility conditions, for example, which could also include things like fog or rain, not just nighttime. So this is really important for being able to install wind farms quickly and get them up and running as fast as possible. So there's an incentive to businesses to be supporting that. I mentioned safety before. Safety is a huge thing, and there's so much time and energy spent on safety when people are operating at sea. So the more you can create technologies that reduce the number of people that need to be on a boat, the better off you are. So there's definitely high incentive to do that, as well as some of this. I think the stakeholder buy-in is important too. You really need to be able to be able to, sorry, I lost my train of thought. I had a thing come up here. The stakeholders are concerned about impacts. And so you really need to be able to demonstrate that you're using the best technologies and that you're addressing those impacts. Improving permitting processes, of course, is also really valuable. Next slide. So I think finally we get to a little bit on effectiveness and standards, and then there's time for questions, I think. Next slide, please. So in terms of effectiveness of these technologies, there is some work that is done on evaluating that, and I've put a couple of example articles here. As I noted, in order to be able to create some of the algorithms and understand how you can use the data from these systems, that there often have to be initial studies that go out and collect other types of data like this PSO here on the bottom. So if you want to know how far a thermal imaging camera can detect whales in different conditions, you have to put someone on a boat, collect those data, and analyze that. So those types of efficacy studies happen. They don't happen as much as I would like. It would be nice if we could do more of those. It's hard because even if you have platforms of opportunity, you only have so many spaces for people on a boat. Again, every person you put on that boat is a safety risk. There's a lot of logistics involved in integrating studies. So this is something that I think is very important for us to be doing more research on, and being able to bring things to the regulators and saying, look, we've determined that this is how far we can detect, or these are the kinds of things we can detect, and this is the real time versus archival kind of ability to analyze data and take action. So this is really important, and some of what we determined in our study for NowRDC was kind of thinking about that, and how can you get things like, for example, if you're going to put a passive acoustic monitor out, you have to have some sense of missed animals, like animals not vocalizing or animals not detected, right? So that takes field work that's sort of dedicated and separate from actually implementing mitigation. Next slide, please. And then finally, we'll talk a little bit here about technology standards. Next slide. So the standards that you set for either the technologies, capabilities, or the distribution, like the methodology, basically the protocols that you're using for the technology, can depend on the question. So for example, like we were talking about earlier, if you just want to know if a whale is within 40 kilometers of a certain location, you can put one PAM system out and detecting the whale will tell you that. If you want to know exactly, or more precisely, where the animal is in space, you'd have to have a different protocol. You'd need a different type or another sort of set of systems in order to be able to do that. So depending on your question, you might have a different set of protocol standards. What's important to regional collaboration is that there are some things that are uniform across multiple studies. Like, for example, if you're putting out PAM systems, you may run them on what's called a duty cycle, which means maybe they're on for 2 hours and then off for 12 hours and then on for 2 hours and then off for 12 hours. And a major reason that you do that is because there's only so much power. So you want to collect enough data over a long enough period of time for the study question, but you can't run them 24 hours a day. And they also collect a lot of data. So you need to be able to actually analyze the data. So if you're doing that and then someone else is collecting at their PAM site and they have a different duty cycle than you do, that, maybe that's good, maybe that's on purpose, or maybe that's a problem because now your data aren't compatible for some meta study that someone's trying to do. So having some idea of how people are setting up their protocols, what the questions are that they're answering, where we can standardize things, even something as simple as time. You can see in the bottom here, bottom right, this is a picture of the standards. So the passive acoustic monitoring data that NIMS is collecting, National Marine Fisheries Service, they've created this database where anyone in the whole world, actually, it doesn't even have to be on the East Coast of the United States, can put PAM data in, and that shows in, I showed you a picture of what one of the outputs of that can look like if you go to their interface. There's a standard way that data need to be formatted to go into that system. So this protocol here is on the bottom. And so that, for example, if people are using time as an indicator, is it time in a particular time zone? Is it universal time? Is it Greenwich Mean Time? What are you basing this on? Because things aren't compatible if you don't know that. So something as basic as, what kind of latitude and longitude measure are you using? Units basically really do matter. So standards are a big deal. Here you can see NOAA and BOEM have come up with some basic standards around how to use passive acoustic monitoring in offshore wind situations in particular. There's a variety of standards around thresholds for marine mammal and other protected species, behavioral response and things like that. But really, we need probably more of this. And there are a number of groups like ROSA, RWSC, and others who are developing more environmental monitoring standards and protocols that will allow for larger scale and comparable studies and use of data to better inform bigger questions about monitoring. And you can see in the bottom right here, this is an example from Navy, but so this is not unique to offshore wind. I mean, there's lots of systems where people are collecting a bunch of different data from different places and different types. Maybe we have eDNA and we have PAM and we have bird radar and all this stuff. And being able to have sort of a step-by-step of, okay, what the expectations are, what are you collecting, how are you collecting it, how are you formatting it, where are you putting it, who has access to it, and how. All those things are actually really important. And that's still somewhat in its infancy, I would say, with offshore wind. So there's ongoing work to get more standards put together. Another issue I'll kind of end with here is on new and unusual technology is sort of the term of art, but there's technologies that are typical and have been used for a long time. Certain types of PAM systems, for example. Agencies and regulators and the general public can be quite familiar with those and feel confident in them. But there's also a lot of work being done to advance technologies right now. And this is a challenge because you want to be able to use a system like, if I said, oh, I have this PAM system that can detect right whales twice as far as a typical PAM system, and I've demonstrated that. I went out in the field, I collected data, I've published a paper. This is showing you that this is the case. You want to be able to use that system and to be able to implement it, as soon as possible. There can be a lot of difficulty in integrating that into current permitting processes or testing, say, a quieter foundation as another example of something like that. All of the requirements around doing that can make it prohibitive for developing better technologies that have less sound production or are better for monitoring. So this is an area that Bureau of Ocean Energy Management and its counterparts in federal government are thinking about and have some regulatory frameworks around them, but it's an ongoing thing to try to work that out. And then also applying it in a way that incentivizes industry to develop such tech. So for example, if you did develop a PAM system that could do what I just said, in an ideal world, that would mean that you could change your protocols for PAM deployment to have less systems out. So, I mean, why would you invest in that in the first place if you're a financial, a commercial company? Because you want to spend less money in the long run on something related to your deployment. But if that doesn't, if the agencies can't implement that, if they just say, well, thanks for spending money and making a better PAM system, but you need to do exactly everything you did with the old PAM system, and it doesn't actually affect the project in a positive way, it's going to disincentivize folks from really investing there. So this is where there's like a push-pull of it. I mean, you need to have testing, you need to demonstrate efficacy, but you also don't want the barriers to be so high that it disincentivizes people from moving forward with this stuff. So this is still an area in flux, something to keep an eye on or weigh in on if you have opinions on it with the regulators involved. And you can go to the next slide. This just has my email address on it. So if you want to contact me directly, you're welcome to. And I'm happy to answer questions that folks have. At this point, I did a lot of talking, so hopefully there's some questions.
Thank you so much, Dr. Corbis. And yes, we already have questions. If people do have more, you can put them in the Q&A, but we probably only have time for one, and we had a bunch of questions about this. So that's great. We can answer this. One of the questions was just, what is the RWSC? But it's the Regional Wildlife Science Collaborative for Offshore Wind. RWSC.org is the website, and a lot of the information that Sarah has shown can be found there. But kind of building off of that, you've talked about how there's so much data being collected by different organizations, by developers, by federal government, by states. To what extent is the environmental data that's being collected being shared within those groups, across those groups? And then where can people find it? Is this publicly available information? And if so, how do people access it?
Very good questions. Yeah, so internally, there have been a lot of improvements too, actually, much of which driven by offshore wind at data sharing across different agencies. One of the really great improvements for offshore wind development has been a work between the Bureau of Ocean Energy Management and the National Oceanic and Atmospheric Administration to use a whole lot of data from all these different places and the different data collection from offshore wind and others to compile all of that and create data layers in GIS formats that help them do siting analysis. So they can look at where there could be conflicts with whales or fisheries or whatever it happens to be, as well as, what you need for offshore wind. You have to have a certain amount of wind, for example. And so you wouldn't site a wind farm where there isn't wind. So this is the kind of thing that they can compile all this stuff together. So these data are being, and the thing internal to the federal government, for example, or state government, depending, like there can be things that aren't shareable, like you have to aggregate certain types of fisheries data because you're not supposed to indicate a particular individual in those data, or tribal data maybe is not something that tribes want shared broadly. There can be things like that, but they can be integrated internally to evaluate based on them, or national security data is another example of that, right? So that stuff is being done. For the general public, there are a number of, if you're thinking about New York, there are a number of different data portals. So usually that's what you're going to want to look for are data portals. And on the East Coast, and I don't know what NROC stands for, NROC, I can't remember, but it was the regional planning body for New England, and then there was a regional planning body for the Mid-Atlantic, MARCO. And those two organizations put together data portals. So if you Google NROC or MARCO, M-A-R-C-O, and data portal, those will pop up for you. Those are interfaces that have collected a lot of environmental types of data, as well as, again, AIS data, which are where vessels are in space and other types of things that were available. Marine Cadastre, which is spelled, the cadastre part, it's all one word, Marine Cadastre, but it's R-E instead of E-R. I'm not sure why, because it's an American thing. But it's the Bureau of Ocean Energy Management and National Oceanic Atmospheric Administration have put together that data portal, which has quite a bit in it. OBIS CMAP is another one, OBIS CMAP. If you Google that, it'll pop up, and it has a lot of marine mammal and sea turtle data in it. On the West Coast, I think the best portals are probably databasin.org and the West Coast Ocean Data Portal, which both of which have specifically set up offshore wind data subportals, basically, for information that might be of interest to people who are doing offshore wind. The data products are really what you're looking at. So data and data products are two different things, right? So the underlying data, if you want to access those, you can look at data products like a density map of right whales, let's say, for example. But then you can also email, they'll tell you whose data it is. So you could email the person whose data it is and you say, you know, I'm studying X and I would like to get access to raw data or some other information that isn't published on this site. And that will help you connect to the right researchers who are doing that type of work. I think state of New York too. I mean, Kate, you could share, you guys have like fisheries databases and things like that, right?
Yes, and we require that projects that contract with the state of New York have to make their environmental data that they collect publicly available. So we've already reached 2 o'clock, so I am going to wrap us up. Dr. Corbis, thank you so much, and thank all of you for joining us for this Learning from the Experts webinar. A reminder that the webinar recording and presentation slides will be available on NYSERDA's website. Our next webinar in the series will be on Wednesday, February 12th. We're going to have speakers from Orrick Law Firm to discuss how state offtake contracts for offshore wind are being designed to incorporate flexible and adaptive terms that manage financial risks. You can register for future webinars through our events page at wind.ny.gov. We also encourage you to check out past webinars in the series on NYSERDA's website and YouTube channel. If you have requests for future topics, we had a lot of questions for this one, so maybe building on this in the future, that you would like to hear about from the series, please email us at offshorewind@nyserda.ny.gov or fill out our Learning from the Experts survey posted on our website. Thank you again for joining us today and see you next time.
Thank you.